Hello everyone. So this is the continuation of our last lecture, lecture 2, where we discussed Coulomb's law, the Coulomb's constant, and we solved some problems. So if you haven't gone through that, please see lecture 2 before coming to this lecture. So we stopped lecture 2 on a numerical problem. Let me start this lecture with the solution of that particular problem. So the problem looked like this. So three charges were placed on the vertex of an equilateral triangle, right? So I believe the charge was minus q, and here it was plus q. The points were marked as A, B, and C. And we need to calculate the net force on charge plus q, which is placed at A, right? So we know that there are two forces existing here, right? One is because of the charge placed at B, which is minus q, and one is because of charge which is placed at C, which is again minus q, right? So you know that these B will exert attractive force on A, right? Because both are unlike charges. So obviously it will have tendency to attract A, right? So the direction of force from B to A will be in this particular direction, right? Similar to C is again a negative charge, and it will also try to attract A since A is of opposite charge. So the direction of force because of C on A is this. Let's indicate this as FCA and this is FBA, right? So now we can say what is the magnitude of these forces according to Coulomb's law. This is K Q upon L square, right? This is again K Q by L square. So now these two forces vectorically are in these directions, and the angle between these two forces is 60 degrees, which is the angle of equilateral triangle. Now you can easily calculate the resultant force, which would come somewhere around here, F resultant, and tell me what is the answer for this problem, right? So according to that the resultant force according to triangle law, it will be something like FBA square plus FCA square plus 2FBA FCA cos of angle, which is cos of 60, right? So the magnitude of FBA is equal to magnitude of FC, which is equal to, let's say, F. The value is this. So it will be like under root F square plus F square plus 2F square into 1 by 2, right? So this is something like root 3F, right? So it will be root 3 K Q square by L square, which is the net force on charge plus Q because of charges at B and C, right? So this is the simple solution for this particular problem. So let's start with today's topics. So yesterday we discussed about Coulomb's law, right? Coulomb's law, which basically says that if two charges are placed at some distance from each other, 2-point charges, they will exert a force on each other, which will be proportional to the magnitude of charges and inversely proportional to the square of distance between them, right? So you would have seen this inverse square law in your gravitation chapter as well. So if you remember, we have Newton's law of gravitation. So if two masses are placed at some distance from each other, the force, gravitational force given them was given by Gmm by d square, right? So you'll be able to correlate these two laws, right? We have a constant, here we have product of charges, here we have product of masses, and inverse square law follows in both of them, right? But in day-to-day life also you experience that gravitational force is a weak force, like between two bodies I'm talking about, because masses and charges, the comparison is different. So if you talk about this particular constant, the value of this constant is 6.67 10 to the power minus 11 Newton meter square per kg square. And the value of this Coulomb's constant is 9 into 10 to the power 9 Newton meter square per Coulomb square, right? So now you can say that the magnitude of electrostatic force, even if I consider unity charge and unity masses, the magnitude of electrostatic force will be very higher than the magnitude of gravitational force, right? So today I'll start with a topic called electric field, right? Electric field. So what exactly is field, right? So field, you obviously know, field is nothing. The field word indicates the region. Basically, it means the region of space, right? So the name itself indicates it is the region of space where the charge can show its effect, right? So let's say, according to Coulomb's law, this is a plus q charge, and this is again a plus q charge, right? And this plus q will exert a force of kq by d square, right? But let's say I remove this particular plus q from here, right? This point is in the name of point is p, and I have removed the plus q charge. So does that mean that there is nothing over here now? So from where the force is coming, there should be something right there. So this is what field is all about. So this plus q charge has its field at the particular point p. Whenever a charge is placed at p, it exerts force on q. So this basically is concept of electric field. Electric field basically means it is the region of space where a charge can have its electrostatic effect, right? So let's understand the definition of field first. How is it defined, right? So before understanding electric field, there is a concept called test charge, right? So test charge or charge under test is basically used for experimentation purpose, and this is always considered a plus unity Coulomb, right? So now electric field is defined as force acting on a test charge, right? Force acting by a source charge on a test charge, right? So let's say this is plus q, this is my source charge, and I have a test charge at a distance d, which is plus 1 Coulomb, right? So this is source charge for which I am calculating the field, and this is test charge, right? So now force on test charge will be given what? K q1 by d square, right? So this is kq by d square, right? Which is an expression of electric field, and it is represented by E, right? So E is what? E is kq by d square, right? And obviously the unit for A is Newton per Coulomb, right? So let's define E is in some other terms as well, right? So suppose there are two charges, plus q and small q, right? Separated by distance. So force between these two charges is kq by d square, right? The field of q at the point D is given by kq by d square, right? And which you can say that it is equal to F by small q, right? So field is nothing but force per unit test charge, right? And hence its unit is Newton per Coulomb. So electric field is nothing but it is force acting per unit test charge. Now you can see that force is depending on the magnitude of charge on which we are calculating, right? If this is the destination charge, the force is proportional to the magnitude of destination charge. But this field quantity, it is independent of the test charge or destination charge. It is independent. It does not have the quantity q in it, right? So field is a general quantity. We can place any charge and calculate field by multiplying it with calculate force by multiplying it with charge, right? So E is not dependent on small q, right? But force is dependent on q. So this is the significance of electric field, that it does not depend on the value of destination charge or test charge, right? So it is defined in that particular way, right? Okay. And obviously, like force, field is also even since force is a vector quantity and field is force per unit test charge, so it is also a vector quantity, right? Now let's talk about direction of electric field. On which direction electric field will apply, right? So let's say this is plus q, right? and we need to find the direction of electric field. Okay, so you know that electric field defined in terms of test charge. So let's say we'll place a test charge, right? So now if we say the direction of electric field at this particular point P, these two are positive charges, and this Q will repel it away from itself, right? But in place of this plus Q, let's say I put a minus Q and then calculate V at this field at this particular point. So now this is a negative charge and we have unlike charge, so it will try to attract, right? So now we can say that the direction of electric field is away from the positive charge, right? It is away from the positive charge, but it is towards the negative charge, right? Right? So this is what concept of field is all about. One. Right. So we just understood the concept of electric field. So let's go a bit into detail, and let's try to find out. Let's try to solve one problem. I'll give it as a homework. Maybe you can give me the solution tomorrow for this. Let's start with the same problem we did for force. So we have an equilateral triangle, right? We have an equilateral triangle. A, B, and C. The length of this is L. So at the vertex of triangle we have charges plus Q. Let's say this is again minus Q, and this is minus Q. Right? So my aim is, what is the electric field at centroid of this triangle, right? This is the problem statement. So you need to get me the answer for this, and then we can discuss this in the next session, right? So yeah. So let's move to the next topic, which is electric field line, right? Field line. This is also called as electric lines of force by Faraday. Electric lines of force, right? So let's say there is a plus Q charge, right? Plus Q charge, plus capital Q, right? So at any point in the space, this R, let's say this R is a variable. It can this can be very near to Q or very far to the Q. So the electric field at any point P will be given out KQ by R square. So you can see that this is inversely proportional to the square of distance, right? So as we go away from charge, the strength of field will keep decreasing, right? You can see from the expression, if you can understand theoretically as well, that the strength of charge, the reason as we go away from each other, the strength and the capability to hold another object or attract another charge will obviously decrease, right? So electric field lines is the indicator, right, of strength of electric field. Like it could tell me that how strong is the electric field at that particular point, or how weak is the electric field at that particular point, right? So what exactly is electric field lines like? So there is nothing called lines over here. So it is an imaginary concept, right? So let's say we have a point charge plus Q, right? We have point charge plus Q. This is a charge, right? So now, as I said, in nearby of this particular charge, in the vicinity of this Q, the magnitude of electric field will be more when compared to the farther points. So electric field lines are the imaginary lines which basically indicates the strength of electric field at any particular point or at any particular region, right? So if I draw vectors from here, right? So I would say that the nearby vector let's say the vector magnitude would give me the strength of electric field. So nearby vector will be of larger magnitude, and then this magnitude will keep on decreasing. Again it will decrease, something like this, right? Again this vector, if I plot in other direction, the nearby vector will be of more length. Again it will decrease, and it will decrease, something like this, right? This vector indicates the magnitude of electric field at that particular point, right? So if I keep on decreasing these lines in different directions, right? So we will see that we get a set of lines, right? So let's say this is plus Q charge, right? As I said, the direction of electric field is away from positive charge. So the lines would look something like this. Let's see something like this. Right? So again it will be in all the directions, right? So now, what exactly indicate the strength of electric field? So if I consider any particular area here, right? So you see, as nearby we are with respect to this charge, the density of lines is higher, right? The lines are more close to each other, right? But as we move away from this particular charge, we see that density of lines are lesser, right? So this line is indicator of electric field, right? So electric field lines are nothing, they are the imaginary lines which gives me the strength of electric field at different points in plane or space, right? So this line will terminate like this from different direction, right? So I might not have drawn it properly, but yeah, this is right. So now let's take a case of negative charge, right? Negative charge. So this is a negative charge, right? So as I said, for a negative charge, the electric field lines will be what? The direction of electric fields is towards sector, right? So the field lines will be something like this. Right? So you can see again, as nearby you are, the density of lines is more. As far you away, as far you go from the density is increasing. The lines are more separated at farther points. The lines are more closer at the nearby points, right? So this is what is electric field lines, right? So we have some properties of electric field lines, right? So before going to that, we also know, or the concept is the tangent at electric field line gives the direction of electric field. Direction of electric field. So now in this particular image, you won't be able to appreciate this particular line, because every line is a straight line, and this is the direction of field. This is the direction of field, you can see. But let's draw these lines for a system, right? Let's say this is plus Q, this is minus Q, right? So as I said, the direction of electric field is away from the positive and towards the negative, right? So this Q will have interaction with minus Q also, and X surrounding also, right? So any field line will move away from Q and it will reach Q, right? Something like this. Right? And again, if we see, and for minus Q it will be going inside this. So now, let's say if I have to find the direction of electric field at this particular point, we need to draw a tangent, and this is the direction of electric field, the net electric field, because of these two charges. At this point, this is the direction, right? So tangent at electric field line gives me the direction of field, right? It's clear? Right. So properties of electric field lines. Properties. First, electric field lines are continuous curves, right? Or continuous lines, curves, okay? And second important property is electric field line cannot intersect each other, right? So let me explain the first one. So electric field lines are continuous curves. So as I showed you, this plus q and this minus q. So if a field line is drawn from this to this, it will be continuous. It won't be like there is a block here, there is a gap here. This is not possible, right? Because in the region of space, we have electric field all around. There is, it's not possible that at a point we don't have electric field, and at another point we have electric field. So this is theoretically and practically not possible. Electric field line cannot intersect each other. But let's say what happens if it intersects, right? And why it can't intersect? So let's say we have a plus q, right? And we have a minus q. So field will come here and go here, right? And let's say there is this q. There is one more point where this field intersects, and this is the point of intersection. So now, if my job is to calculate the direction of electric field at this intersection point, now we can say that here, because of this curve, the direction will be this, the tangent will be this, and because of this curve, the tangent will be this, right? For the same point, we have two directions of electric field, right? Which is not possible, right? The resultant electric field at any point will have unique direction, right? Because of the combined effect, and hence electric field lines cannot each other, because if they does, there won't be a unique direction of electric field, right? And third, electric field lines cannot form closed loops, right? So we will discuss this in detail in later chapters, but as of now, you can just understand that if a line has originated from plus q and they have entered minus q, it can't revert back and go to plus q, like you would have seen somewhere in magnetic field lines or things. But electric field lines cannot form this closed curve, because you know, you might have studied in class 11 that if for any conservative force, work done in a closed path is 0, right? So theoretically, this electric field lines cannot form closed loop because this force is a conservative force, right? Yeah. Right. So we just studied electric field lines and how we draw electric field lines for a point charge, system of charges, and things like that. And how does electric field line can give me the magnitude of electric field, not magnitude, the strength of electric field, right? So related to that, we have a concept called electric flux. So electric flux basically indicates the flow of electric field, right? It basically indicates the number of lines passing through some unit area or given area, right? So let's go back and let's go back to class 11 and think about equation of continuity. You would have studied in fluid mechanics. So let's say this is the outlet, right, which has area A, right? And it has liquid flowing out with a velocity v, right? So what is the net liquid flowing per second, and what it depends on, right? We know that the net volume of liquid flowing per second is given by area into velocity, right? Area into velocity, right? So if area is higher, we can supply more liquid in per second, right? Or if velocity is higher, the same way around, right? So this indicates the rate of flow of liquid, right? So similar to this concept, we have a concept of electric flux, which is for electric field lines, right? So let's say we have an area, right? Let me draw an area. So this is an area, right? We indicate area by S. We denote by symbol S, right? So let's say electric field lines are crossing this area. So number of field lines it would allow to pass, or it would number of field lines which will pass through this will depends on two parameters. One we obviously discuss is strength of electric field, right, which is E. Right? But one more parameter which we have is S, which is area. Right? So as bigger is the area, we will have more space to accommodate number of field lines. Right? And same goes with magnitude of electric field. As greater the magnitude of electric field, we have more number of field lines. So electric flux is indicator of number of field lines passing through this particular area, right? And electric flux, which is denoted by symbol phi, is given by E into A, right? Which is electric field. E is nothing but electric field intensity, right, into area. Right? So as I said, electric flux is indicator of number of field lines passing through the area, right, which is in turn the indicator of two things which would depend on the magnitude of electric field and then the area, right? So let me put it like this now, right? So this area is basically area vector, right? What exactly is area vector? So area vector is nothing but, let's say this is the area. If we draw a normal to this particular area, this normal has a direction now which is perpendicular to this area. So this normal gives area a direction. So this is called as area vector, right? So let me put it like this now. So now let's say, again let me draw an area. This is an area, okay? Previously the field lines were passing normally to this particular given area, right? Let's say that now field lines are passing at some angle, right? These are field lines and they are passing at some angle, or let's say theta is the angle, right? So the field lines which are actually entering this area, which are actually of my interest, is the component which is normal to this area, which is the horizontal component, right? Which is what? E cos theta, right? And obviously the net flux here will be E cos theta into area, which is S, right? Clear to it? So now we know the flux is given by Es cos theta, right? So in terms of vector, I can now write it as E dot S, dot product of electric field intensity and area vector. So this is what is electric flux, right? Okay. So now let's say we have a continuous block, right? It has multiple small areas, right? Let's say this area is delta S1, then we have delta S2, delta S3, and something like that till delta Sn, right? So net flux, let's say electric field is E, right? Or maybe let's say this is E1 here, E2 here, E3 here, or En here. So net flux will be what? It is summation of all the fluxes, right? So it is summation of what? Let's say summation of all the fluxes from I equal to 1 to n, right? Okay. So this is for the discrete mass systems. Again, if you see the continuous mass system, this will become an integral form, right? So this will be the net flux, right? Okay. So yeah, flux is a dot product of two vector quantities, which is electric field density and area. Hence flux is a scalar quantity. Do remember that flux is a scalar quantity, and the unit of flux is Weber, right, which is Wp. So this is clear about flux, right? Okay. So after flux, we have a concept of electric dipole. So the name itself says that this is a dipole, right? So dipole means we have two poles, two different charges, right? So dipole is nothing but two opposite nature charges separated by some distance. Two equal and opposite charges separated by some distance is what? Dipole. Okay. So let's say minus q plus q. These two charges are equal and they are separated some distance d. So this is nothing but electric dipole, right? Now you can think in chemistry also. You would have seen dipole. Let me give you an example, right? So this is the structure of water molecule, right? This OH and H. So you say that oxygen is electronegative. So it has tendency to keep the shared pair of electron towards itself, right? So it will have a negative charge, right? And oppositely this H will develop a positive charge. You say that these two are same amount of charge separated by some distance. So this is a dipole here, right? Again a dipole will be created here as well, right? So to define dipole, we have a vector quantity called dipole moment. Dipole. And dipole moment is represented by P vector, right? P. So dipole moment is the product of magnitude of charge and distance. Simple. Right? Product of, this is a normal product, don't go for cross or dot. This is a normal product, and it is the product of charge and distance. And this, according to the convention, the direction of dipole moment is always from the negative charge to the positive charge. So the direction of dipole moment is from negative charge to positive charge, right? So in this particular example, direction of dipole moment is this, right? Okay. So now we have studied about how can we calculate electric field for a unit charge, for a point charge. So for a dipole, how can we calculate the electric field is the next topic, right? So let's say we have a dipole minus q plus q. This is a dipole. So now there are two positions to this dipole, right? This is the axis of dipole, and we can place one third point P along the axis of dipole. So this is what we call an axial position. And if we place a point P orthogonal to this dipole, let's say P here, this we call as equatorial position, right? And this is axial position. So we will be calculating electric field at axial position as well, equatorial position. So now the topic is field due to dipole along its axial position. So we'll calculate the field due to dipole at axial position, and then we'll also calculate the field at equatorial position. Okay. So let's say this is a dipole minus q plus q. For convenience, we say that this is separated by a distance. Let's say this distance is given by 2a, right? 2a, and from this is my point of interest P, which is located at a distance r from center of this dipole. So these two charges placed at A and B system of dipole, and this is my point of interest, which is P. So now we have two types of field acting here. One is because of this plus q, and another because of this minus q, right? So now both fields are different magnitudes, right? So now from A to B distance, you can see this is A, since this is 2A. So A to B distance is what? Sorry. A to P distance is R plus A, and B to P distance will be what? R minus A, right? So now you can say the electric field because of A on P will be what? KQ by R plus A square, right? KQ by R plus A square, right? And electric field by B on P will be given what? KQ by R minus A square, right? So you know which is greater among these two, EAP or EBP? Which is greater? So you know that R plus A is obviously greater than R minus A, right? And hence EBP is greater than EAP, right? Because since it is in the denominator. So EBP is greater than EAP, right? So the direction of EBP will be away from positive. The direction of EBP is this, and direction of EAP is this, right? So net direction is towards EBP. So net field is what? Net field is EBP minus EAP, right? Which is, if I take common, it is KQ 1 by R minus A square minus 1 by R plus A square, right? Right? So now if I evaluate this and take LCM and things, it will be something like KQ by R square minus A square whole square into what? Into 4R A, right? This is what it is, right? So if I rearrange it, it will be what? 4 K Q R A upon R square minus A square whole square. Okay. So now we assume that this particular R is very greater than the distance between these two dipoles, because generally dipoles are very small systems and the distance is very small. So this particular R is very greater than A, right? So if R is very greater than A, R square minus A square won't have its contribution, right? Like let's say we are doing let's say we are doing 1000 square minus 0.1 square. So we can still ignore this 0.1 because this is very negligible. This is something of that sort it is, right? So now if I say this net electric field will come around 4 K Q R A upon R square, which is R4, right? So now R and R will cancel, so it will be 4 K Q A by R cube, right? Now I can rearrange it and I can write it like this: 2 Q 2 A K by R cube, right? So this Q into 2 is nothing but dipole moment, right? So this is nothing but 2 Kp by R cube, right? 2 Kp by R cube. So electric field due to dipole at axial position is given by 2 Kp by R cube, right? Let me write it like this. So let me put minus Q, 2A plus Q, and from a distance R from here at point P, the electric field is given by 2 Kp by R cube. You already know R is the distance from the center to this dipole. K is nothing but K is over 1 by 4 pi epsilon naught, and P is what? Dipole moment, which is Q into 2A, which is charge and distance, right? So this is the field due to dipole on axial position, right? So next is the calculation of field due to dipole at its equatorial position. But before that, we should know that this electric field is now inversely proportional to the cube of distance, right? Cube of distance from this dipole, right? So this is the point to note here, right? Because other parameters here are constant. So one homework for you will be, you need to calculate the electric field due to dipole at equatorial position, and then we can discuss that in next lecture. Okay? So we can stop for today with this. Thanks a lot.